Hi, I am Madam Rosmaya. In this video, we are going to discuss on stopping potential and energy of a photon. Okay, stopping potential. So what is meant by stopping potential? So look at this animation. So we are going to watch two animation. So watch this animation. So the voltage here start from 0. The current still shown here, even though the voltage is 0. We increase the voltage, then the current increases. So this is the graph until it reach maximum. So the current reach maximum. Even though the voltage continue increasing. Okay, so I repeat the animation. Okay, voltage 0 across the cathode and anode here. Okay, the current still shown here, the reading of emitter. When increase the voltmeter by sliding the potential divider, so the current increasing until maximum. Even though the voltage still continued to increase, but the current no more increase, become maximum already. Okay, so why this happen? So we divide into 3 parts. So the first part here, okay, for the graph photoelectric current against potential difference, the graph here doesn't start at 0 at the origin, so start at some value here. Okay, so when the potential difference is 0, a photoelectric current can still be observed. So we plot the graph start from here, okay, not at the origin. Okay, so why this happen? Okay, so why this happen? The reading, the emitter still give reading even though the voltage across the cathode and anode here is 0. Okay, so why? Because when the light is incident on the cathode, electrons are emitted with different kind of kinetic energies. So ranging from 0 to maximum value. Okay, so the one that energetic, when the potential difference 0, so only the very energetic electrons able to arrive at the anode. Okay, so not all are able to arrive at the anode. So when the electron are able to arrive at the anode here, so then the current, because this is the complete circuit, so the current can flow through the circuit. Okay, so this is why the initial photoelectric current here not 0. Okay, still got reading here. Okay, so any problem with this one? The first part? Okay, no question. So means understood. So we go to the next part. Next part, the increasing part. Okay. So the photoelectric current increases as the potential difference is increased. So we increase the voltage across the cathode and anode here by sliding here the rheostat. Okay, by sliding the rheostat. So we increase the voltage. So what happened is the photoelectric current increases. So why this happen? Okay, so when the anode is at a positive potential here, so the emitted electrons will be accelerated towards the anode. Okay, so hence more electrons are able to arrive at the anode. So just now 0 potential. Now the potential increases. Okay, we increase the potential difference across cathode and anode. So here the anode become more positive. Okay, so more electron will be accelerated towards the anode. So therefore the current increases. The photoelectric current increases. So this is the part. Okay, any problem with the second part? So if no problem, so that's mean you understood. Okay, next we go to the third part. Okay, the third part. So the third part, as the potential of the anode is increased, more and more electrons will reach the anode until it the maximum here. No more, it turn to be maximum photoelectric current. So the third part, we are going to discuss the third part. So why this happened? Okay, so why the photoelectric current reach maximum value? Okay, and then remain constant even though the potential difference is increased further. So the reason is at a certain potential, all electrons emitted. So all the electrons emitted from the surface of the metal already. Okay, so the anode giving rise to the maximum photoelectric current. Okay. Further increase in the potential difference can no longer increase the number of electrons arriving at the anode. Because here all the electrons emitted already from the surface of the metal. So hence the photoelectric current remains constant at the maximum value. Okay, any problem with this part? So from what we've discussed before, the emission of the electron from the surface of the metal involve the one-to-one interaction. So means all the electrons inside the metal here are already liberated, okay, to the surface of the metal. Okay, so if we use the same light but we make it brighter, or in other words, we increase the intensity. Okay, so what happened? This is what happened lah. We will increase the maximum value of photoelectron for each trials. Okay, so the maximum value of the photoelectric current increases with the intensity of the incident light. Okay, remember the meaning of intensity. To imagine the intensity, you can imagine the brightness lah. So if the incident light here becomes brighter and brighter, so what happened? You increase the photoelectric current, maximum photoelectric current can be reached. Okay. So this one, any problem or not? Okay, but remember we use the same light. So we're not changing the light. Example, if we use UV, then we use green light and so on. We just use one type of light with one wavelength. Okay, that's mean it has one wavelength. We only change the brightness of the light. Okay, or in other words, intensity of the light. Okay, so we get the higher intensity, so higher maximum photoelectric current can be reached. Okay, so why this happen? When the intensity of the incident light increases, the number of photons per second incident on the cathode increases. So the larger number of photons per second incident on the cathode increases. So because of the one-to-one reaction, okay, subsequently the rate of emission of the photoelectrons increases. Okay. So now refer to the second animation. We reverse the battery. Okay, reverse, or in other words, reverse cathode become anode, anode become cathode. So what happened? Okay, so the photoelectric current decreasing. Still has value but decreasing. As we increase the voltage here, it become negative voltage. So it stopped until no more current flow. Even though you increase further voltage, still no more current flow. Okay, so this happen when the batteries in the photocell circuit are reversed. Okay, so we reverse the cell. So what happened? The anode become negative and the cathode become positive lah. Okay, so in other words, cathode become anode, anode become cathode. Okay, so I repeat the animation again. Okay, so the voltage increase, the current decrease. So refer to the graph here, decreasing in photoelectric current until the current stop. The current stop at certain value of voltage. If you continue the voltage or potential difference, still zero, no more current. So we divide into two parts. Okay, the first part is the decreasing part. The micrometer reading increases. The micrometer reading decreases. So why this part happen? So this part happen. So the anode now become negative. Become negative. So it become first slightly negative. So we increases the voltage. So initially it's only slightly negative. So some electrons have enough energy to reach the anode. That's why giving rise to the photoelectric current. So still got reading in the emitter. Okay, got current, photoelectric current flow through the circuit. Okay, so when we increase further, so that means that the anode become more and more negative by increasing the voltage. So the anode become more and more negative. So fewer photoelectrons can now reach the anode. So therefore, the photoelectric current decreases. Okay. And we know that the electron emitted here is negative charge and the anode is negatively charged. So negative, they repel. So when the larger the anode negatively charged, the charge. So therefore, the repulsion force is greater and greater when you increase the anode. When the anode made more negative, so that means the repulsion force become more and more or increases. So that is what happened, why the photoelectric current decreases. Okay, any problem or not for this part? No, Okay, so now at the another part is at the point here, So it's become zero until we increase the voltage until the emitter shows zero reading. So even though we further increasing the voltage across the cathode and anode here, but the emitter still show zero reading, shows zero reading. Okay, so this happen when the slider is at particular position. The micrometer start to show readings, zero readings. So why this happen? Okay. So we call the voltage at this position as a Vs, stopping potential. Okay, so at the stopping potential, even the most energetic photoelectrons do not reach the anode. So hence the photoelectric current is zero. So the repulsion force here is the greatest. So no electron manage to reach the anode. Okay, because the anode here become negative and negative, more negative until no more electron emitted by the metal here can reach. Even the most energetic photoelectrons, okay, cannot reach the anode. So the potential difference across here at this moment is called stopping potential. So the stopping potential is the potential difference that stops the most energetic photoelectrons from reaching the anode. Okay, any problem with this part? No, So we go to the next part. This is the animation shows how the electron here, okay, it no longer can move when the anode here we make more and more negative. Okay, so remember one more, we make this negative when we change the cell here. Okay, positive to negative. So this is positive. Now we make it negative. Okay, we make negative, no more current can flow. Okay, so this animation given here very fast. Hopefully you can understand the whole process. Okay, so the conclusion here is the potential difference across the cathode and the anode when there is no photoelectric current is known as the stopping potential. Okay, so now the calculation part. Okay, the calculation part. So we are going to use the principle of conservation of energy. Okay? So the energy, the maximum kinetic energy we call Kmax of the photoelectrons is equals to the work done against the opposing potential. Okay? So the maximum kinetic energy equals to the EVS. So if this is the Kmax, maximum kinetic energy, here we use stopping potential. And then Kmax is half mv max squared. So we can calculate the maximum speed for the electron. Okay, equals to the EVS. So an electron which is emitted from the cathode and moves towards the anode will stop when all of its kinetic energy has changed into electric potential energy. Okay? So the kinetic energy is converted to potential energy. Okay, electric potential energy. So this is what we use to derive the equation for the stopping potential. So become Kmax equals to EVS. Okay. So the stopping potential is independent of the intensity of the light. Here. So if we use the same light but increase the intensity of the light, okay, the graph maximum photoelectric current will show two different value, but the stopping potential here reach at one point. If you reverse the battery cell, okay, the terminal of the battery. So we still get the same value of stopping potential. Okay, any problem with this graph? Understand, So just now we show until the positive part of the graph. So now if you continue drawing the graph, so it reach at the one point x-intercept. The same voltage Vs. Okay, now the Vs will change only if we use different metal. Different metal. So if you use caesium and potassium here, okay, the metal used as a cathode. Okay, and the cathode, when we change the cell, the terminal of the battery, so this part, the negative part, we get different value of stopping potential because different material use, right? For the metal, different metal use. Okay, if same metal use, you get same Vs, different photoelectric, maximum photoelectric current if use high intensity for the same metal. Okay, next. So stopping potential depends on the cathode material and also on the types of wavelength use. Okay, so different cathode materials have different stopping potentials. Why? So because caesium has a smaller work function compared to potassium. So hence photoelectric electrons have higher maximum kinetic energy and therefore a higher stopping potential is required. Okay. So remember the work function we discussed before, the minimum energy absorbed by the electron in the metal, so that it managed to escape from the surface of the metal. So caesium has smaller work function, so it just need smaller energy to be absorbed to escape from the surface of the metal. So therefore the photoelectron have higher maximum kinetic energy. Okay. So if the light we use have same density but different wavelength, okay, different wavelength. Different wavelength means different frequency. Okay, so let's say we use UV light and green light. Okay, UV light and green light, but with the same intensity. So the same metal. Okay, same metal, same intensity, different frequency. Okay, we use UV light and green light, for example, with different frequency. So what happened? We also get different stopping potential. Okay, stopping potential here, different. Let's say F2 and F1, different frequency. So it reached the maximum photoelectric current, the same point, okay, at the same position here. But the PS will be different. PS is stopping potential. Okay, so you must know the difference between the three graphs just now. When we use different material for the metal and different frequency and different intensity. Okay, so you advised to how to know how to distinguish, okay, between the three types of graph. Okay, next, you can do already checkpoint 24.1. Okay, so we've done checkpoint 24.1. Continue with the yesterday one. Okay, so the relationship between Vs and F, we will continue after discuss the energy of a photon. So we go to energy of the photon first before we continue the relationship between stopping potential and the frequency. So this graph we hold on for a while. So we go to energy of a photon. Then tomorrow we can continue combine them, energy of a photon and the stopping potential. Okay, energy of a photon, we use Einstein equation. This is called Einstein equation. E equals to hf. Okay, energy of a photon, h times f. So f is a c per lambda. Okay, from the equation v equals to f lambda. So the v, the speed of the light, we use c instead of v. Okay, become hc per lambda. So h is a Planck constant. The value is 6.63 or 6.626 times 10 to the power of negative 34 joule second. And frequency of the photon or any electromagnetic radiation. And the c is 3 times 10 to the power of 8 meter per second. So this is the speed of light in the vacuum or speed of electromagnetic electromagnetic radiation. So lambda is the wavelength of photon. Okay. Then photon move at the speed of light. So that's why we use the c value 3 times 10 to the power of 8 meter per second. So if we have n photons, so n times hf. Okay, n times hf. Okay, so we try one example, simple example. Calculate the energy of an individual photon of yellow light. So yellow light have frequency 2.73 times 10 to the power of 16 per second. Okay, or hertz, the unit can be in hertz also. So you are given the frequency. If you are given the wavelength, you need to, if you are given the wavelength, so you need to calculate the frequency using V equals to F lambda or C equals to F lambda. So now you are given frequency, you straight away use E equals to HF lah, not HC per lambda. Okay, so substitute the H Planck constant 6.626 or 6.63 times 10 to the power of negative 34 joule second. And then the frequency is given 2.73 times 10 to the power of 16 per second. So you get 1.81 times 10 to the power negative 17 joule. Okay, so this is the energy of the individual photon of yellow light. Okay, so in 1901, Max Planck hypothesized that the energy radiated by a black body must be an integral multiple of a constant times the frequency. Okay? At that time, H from name after this Max Planck lah, Planck constant. So the H Max Planck do experiment and found the value of H. So that is energy is quantized. Okay. So in 1905, Einstein extended this hypothesis to explain the photoelectric effect. Okay, so Einstein proposed that energy of light is quantized and exists in discrete packets or quanta that are called photons. Okay, so the energy of a photon, sometimes we write it in terms of electron-volt. Okay, so the electron-volts, in short form, we use EV, capital letter V. Okay, so what is electron-volt? Electron-volt is the energy of a photon, but we express it in the unit EV. The equation also EV lah, EV. So for 1 electron-volt, can be defined as the kinetic energy gained by an electron which has been accelerated through a potential difference of 1 volt. So the electron will be 1.6 times 10 to the power negative 19 coulomb. So E is the charge of electron. So V is the potential difference across the cathode and anode. Okay, so 1 EV equals to electron charge times 1 volt. So we get 1 EV. So if we convert to joule, so we substitute the electron charge 1.60 times 10 to the power of negative 19 coulomb. And then potential difference, volts here, volts is 1 joule per coulomb. So we can cancel the C here. So we get electron-volt in terms of joule, which is 1.6 times 10 to the power of negative 19 joule. Okay, so you memorize this. 1 electron-volt is equals to the 1.60 times 10 to the power of negative 19 joule. So this is the relationship between electron-volt and joule. So you use this to convert energy of a photon from joule to electron-volt or from electron-volt to joule. Okay, example, we try this. Calculate the energy of a photon of red light of frequency 4.30 times 10 to the power 14 Hz. And then also calculate the energy of a photon of blue light of wavelength 476 nanometer. Okay, for the red light, frequency is given. So the energy is E equals to HF. So the frequency is given, so we can use directly this equation. Okay, so we substitute the value of H and frequency. So the answer is 2.85 times 10 to the power negative 19 joule. So if you want to convert it to electron volt, so you divide it by 1.60 times 10 to the power negative 19 electron volt. So you get the answer in electron volt. So 2.85 times 10 to the power negative 19 joule is equals to 1.78 electron volt. So how to memorize whether to multiply by 1.6 times 10 to the power negative 19 or divided by 1.60 times 10 to the power negative 19? It's very easy how to memorize it. This is a smaller value. If not in standard form, you will get 0.0000 until 19 zeros. So to convert to electron volt, so you get in easier form to observe 1.78 electron volt. So without the times with smaller value here. So not in the 0.0000 So the zeros here too large if you write in joule, energy in joule, too small. So that's why we convert it to electron volt. So you will get easier value to be observed. So if you multiply if you think of the logic, if you multiply by 1.60 times 10 to the power negative 19, you will get a smaller number. So remember that electron volt is in the form which can be observed in the what not in the smaller in value lah, like this one. This is smaller in value. Okay, so we do question B. Question B, a photon of blue light of wavelength 476 nanometer. So now wavelength is given. So if wavelength is given, F you use C per lambda. Okay, so F C per lambda. So you substitute H, Planck constant 6.63 times 10 to the power negative 34. Then C is speed of light 3 times 10 to the power 8 divided by lambda wavelength 476 convert to meter times 10 to the power negative 9 meter. So the answer is in joule, 4.18 times 10 to the power negative 19 joule. So this is too small. Okay, so you convert to electron volt. Convert to electron volt, so you divide it by 1.60 times 10 to the power negative 19. So you get the answer in electron volt, 2.61 electron volt. So this is energy of a photon of blue light, 2.61 electron volt. Okay, any problem with the example given? Okay, that's all for the video. Thank you for watching, and don't forget to subscribe my video if you like the video.